All right, we're going to talk about probably our last topic in 21B, the idea of polar coordinates, which is something you will use quite frequently in 21D, maybe a little bit in 21C. And you may have even seen this before if you took a trig class. They may have introduced you to this idea of polar coordinates. And all we're talking about here is just a different coordinate system for locating a point in space here, in two-dimensional space here. So Cartesian coordinates or rectangular coordinate system, how do we get to a point x, y? We move horizontally in the x direction and then vertically in the y direction, and that takes us to the point. In polar coordinates, we think about it this way. I could get to the same point x, y, rather than going horizontally and vertically. Suppose you were facing the positive x-axis, so your angle is 0. Remember in trig, theta equals 0 is facing the positive x-axis. So you're facing that direction. Turn yourself so you're facing this point and just go straight to the point, a distance r. So in many sense, it makes more sense in polar coordinates. If you think about, like, how do you, if you were going to walk from the origin to this point, not you wanted to get there quicker, you wouldn't go horizontally and then vertically. You would just turn whatever direction you need to walk and you would just move in that direction. So it does make a lot of sense. If we put those two pictures together, we can come up with what we call conversions from Cartesian to polar coordinates. So these are just equations that happen to be true that relate those two systems. You have a right triangle here, so the most obvious relationship is this is x, this is y, x squared plus y squared would equal r squared. If you used a trig function and you said cosine of theta is x over r, and then solve for x, x will be r cosine theta. If you do something similar, y will be r sine theta, using the opposite side. And then theta itself, the tangent of theta is y over x, which means theta is the inverse tan of y over x. So these conversions are good to know. We're going to see they become in handy when you're trying to go back and forth between polar and Cartesian coordinates. Okay, and then one other note about polar coordinates: r is a distance that you walk from the origin to get to your point. But we can talk about a negative r value. So if you had a negative r value and you had some angle theta that you were facing this direction, negative r just means instead of going forward by that distance r, you would go backwards. So if this point was r theta, directly opposite that would be negative r theta. And because of that, and because there's more than one angle that will take you to a certain position, I guess, relative to the origin, you can actually have an infinite number of polar coordinates for every Cartesian coordinate. So if, let's say I had the Cartesian coordinate, this is x, this is y, 0, 4, right here on the y-axis, let's come up with 3 different polar coordinates. Probably the easiest way would be, if, remember, you're facing 0, that's your default, is facing the positive x-axis. So if you rotate by an angle of pi over 2, you're now facing the positive y-axis, and then move out a distance 4, that would be your r value, the coordinate 4 pi over 2. So r comes first and then theta. So it's 4 pi over 2 would correspond to the same point, 0, 4 in Cartesian coordinates. Alternatively, you could get to this correct angle if you rotate it in a negative way by 3 pi over 2 and then walk out 4 units. So 4 negative 3 pi over 2 also works. And then another way, what if I rotate negative pi over 2 so I'm facing the negative y-axis? If you walk backwards 4 units, meaning you make your r value negative 4, that would also take you to the same point. Okay. How about 1, 1 over 1 up 1? easiest way would be to just rotate by an angle of pi over 4, and r would be, by the Pythagorean theorem, the square root of 1 squared plus 1 squared is root 2. So you'd have root 2 pi over 4. You could rotate to this angle going in a negative way, negative 7 pi over 4, and walk out root 2. You could also rotate to 5 pi over 4, which is facing this direction, and instead of going positive in this direction, in other words, instead of going forward, go backwards, and that would take you to 1, 1. So you'd have negative root 2, 5 pi over 4. So one skill to be able to do is go back and forth. So we practice there locating points and coming up with polar coordinates for a particular point. We also can take an equation in Cartesian coordinate system and convert it to a polar equation. So the line x equals 3, which is just a vertical line, this is where the conversions come in handy. If I replace x with r cosine theta equals 3, divide by cosine to solve for r, and of course 1 over cosine is secant theta. The vertical line x equals 3 in polar coordinates is the equivalent to r equals 3 times secant theta. Sometimes you can kind of see why that would be true. If you take any point on this line, I took a random point here, and think about r would be this distance, which is going to vary depending on where you pick that point. This will always be 3, and this angle will always be theta, and you can see the relationship, right? The secant of theta is going to be r divided by 3. So now the line y equals x, a line passing through the origin at an angle of pi over 4, if we do our conversions, y is r sine theta, x is r cosine theta, move it over and factor out an r, you kind of get two results here. R equals 0, which, okay, if r is 0, that just means you're not moving anywhere. You're at the origin. And that is a point that is on my line, but it's clearly not the whole line, right? So if I look at the other part of this, sine theta minus cosine theta equals 0, which says sine theta equals cosine theta, the only angle that would make that true is pi over 4. So theta equals pi over 4 is actually all we need. And this equation doesn't have r in it. And the reason why is because if you're facing the angle pi over 4, you can let r be any distance, and it's going to take you to a point on that line, including negative values, right? Negative r values. So if your equation is just written in terms of theta, what it means is r, well, I wrote it right here, r can equal anything, okay? Any r value you choose is going to give you a point on that line. Now this line, y equals 2x plus 1, is not going through the origin. If I use my conversions now, I'm going to be able to solve for r. And I get 1 over sine theta minus 2 cosine of theta. So certain equations, right? In rectangular coordinates, I'd say this looks a lot cleaner than the corresponding equation in polar coordinates. But there are times when polar coordinates, I think, are nicer than rectangular coordinates or Cartesian coordinates. X squared plus y squared equals 16 we recognize as a circle with a radius of 4. And x squared plus y squared, recall, just equals r squared. So if you knew that conversion, you could actually just go straight from here to here. What I did was I plugged in x was r cosine theta, y was r sine theta, squared them both out, factored out an r squared, cosine squared theta plus sine squared theta equals 1. That gave me r squared equals 16. Now, mathematically, r could be plus or minus 4, but you really just need it to be, you can just have r be 4, because if theta can be anything, as long as you move 4 units away from the origin at any angle, you're going to get to every point on that circle. So a circle like this has a very simple equation. It's just r equals 4. It's just the radius of the circle. okay? X squared plus y minus a half squared equals 1/4. This would be a circle centered at 0, 1/2 on the y-axis. Remember, the radius would be the square root of 1/4, which is 1/2. So it's going to stretch up to 0, 1, and it's going to come down to the origin. So this is the circle. Let's see what it looks like in polar form. X is our cosine theta, y is our sine theta. I have to expand this out, FOIL this out. You get the 1/4 to cancel. If I factor out an r squared from these two terms, I get cosine squared plus sine squared, which is equal to 1. So that's going to leave me with just r squared minus r sine theta. Factor out the r. Once again, you do get r equals 0, but that's just basically describing the origin, which is a point on the graph, but it's not the entire graph. So let's look at the other result, which is r equals sine of theta. So this circle, centered at 0, 1/2 with a radius of 1/2, actually has the polar equation r equals sine theta, which is actually not too bad, right? That looks a little bit easier to work with than the rectangular form. And if you're curious, r equals cosine of theta would give you the same circle on the x-axis, centered at 1/2, 0, with a radius of 1/2. Okay. What about going the other way? Sometimes you have to convert back to Cartesian. R equals 4 cosecant theta is the same as r equals 4 over sine theta. If you multiply the sine theta over, r sine theta equals 4, and then you would want to recognize that r sine of theta is the same thing as y in Cartesian. So this is just the horizontal line, y equals 4. R squared equals sine theta times secant cubed theta. Let's move the secant cubed. That's really 1 over cosine cubed. Multiply this over. R squared cosine cubed equals sine theta. And you're kind of always thinking about these conversions. If I see a sine theta there, if I had an r next to it, then I could change that into a y. So let's multiply both sides by r. Now this can be replaced with y, and now I actually have r cos, if I break this up as r cosine theta, another extra r cosine theta. Those are all x's, so this would be the same thing as y equals x cubed. Finally, there are some polar graphs that don't convert very nicely into Cartesian coordinates. And so if you get one of those and you're asked to graph it, I just wanted to show you a kind of a popular one. What you can do is always you can pick values for theta and then figure out what your corresponding r values are. So what I did was I picked some common angles that I can plug in and evaluate the sine of. In fact, I chose pi over 6 because the sine of pi over 6 is 1/2. And I get a nicer r value, 1 minus a half. You could choose, the more points you choose, the better. So I could have chosen pi over 4 and pi over 3. I would just have messier r values. Anyhow, if you take these r values and plot them, and to do that, you can download paper called polar graphing paper. And what it looks like is the x and y axes, and then there's usually a bunch of concentric circles, because when you plot, you're always looking for a certain angle and you're looking for a certain distance, right? So I can plot 0, 1 is right here when theta is 0. When theta is pi over 6 along this line, my r value is 1/2, so you move a half a unit out. When theta is pi over 2, r is 0, so you're at the origin. 5 pi over 6 is here, your r value is 1/2, so you go out 1/2. At pi, which is over here, you go out 1 unit. 7 pi over 6, I get 3/2, so you're going to go 1 radius plus another half of a radius. 3 pi over 2 is 2 full units, and then 3 pi over 2, and then back to 1. And if you interpolate and kind of imagine some other points in between there, you do get a heart-shaped graph, which is referred to as a cardioid. I always say it makes a good Valentine's Day card, right? Graph looks just like a heart. And there's others. There are graphs that look like roses where they have like leaves. If you've seen some of those, those are also very common. I don't think at this point you would really need to know too much. I think you just need to be aware that some of these graphs you would have to graph by plotting points, and converting to Cartesian coordinates would not help. Okay. And then the last video we're going to do after this, we're going to talk about you doing calculus with polar equations.